All right, welcome to Module 4. This is Part 3, talking second and then third law of thermodynamics. So based on direction of physical flow, something that is a hot source will move towards a cold sink. So there is a spontaneous action that will move from warm towards cold in an isolated system. We think of this as the laws of dispersion, right? So temperatures will move towards the lower temperature and it will mix until they find a balance, right? And so we have the nice little ice cube and it has minimum amounts of entropy. It's stacked really close together and it's going to move towards the water, so the cold water in the set. So everything is kind of said backwards when we think of things within our systems, because we often think of them as how they affect us. But in actuality, what's happening is we're affecting something else. When you touch something that is cold, the cold and you are interacting, but your heat energy is leaving you and moving towards the cooler object to try to share and create a sense of equilibrium, a balance, some temperature in between the two where you both cool off and find the same temperature within yourselves. This also goes into the ice cube concept. So when we talk about the ice cube concept, we often think that the ice cube is cooling the drink down, but that's not true. The drink is doing it the other way around. The drink is acting on the ice cube, melting the ice cube, right? So it's the other way around. We reverse things in our mind, but the proper way to think of it is that the liquid is acting on that solid, right? Because that's the hot source and it's moving spontaneously towards the cold sink. So when we talk about things like smart buildings, one of the first changes that we've begun making in homes that we're trying to build in an intricate, smart way is to move the heating systems off the walls. We don't want radiators on the outer walls that touch the outside of the house, because that means that the heat will pool and stay up against the window system, since the cold sink is what's outside of the windows and doors, right? And so we want to move those to the interior of the building, and therefore the heat can then flow towards the window systems, the cooler sinks, right? Because that's spontaneous motion. Whenever we try to do something in the other direction, where we have to try to make the cool act on the warm, we have to do it and add a lot of work. This is why air conditioning units, air conditioning systems tend to use so much more energy than heating systems, because the heating systems get to use the second law of thermodynamics, where it will spontaneously flow towards those cold sinks and fill them in. Where with air conditioning systems, I have to force my cold into these hot sources, and these hot sources are constantly trying to act upon my cold sinks. So keep those things in mind. This is part of these important bits of thermodynamics. One of the things that can come up in this little bit is just talking about the concept of maximum efficiency. One of the ways that I can find how efficient something that's doing a heating system is by taking the temperature that's hot minus its temperature cold, divide it by the temperature of heating, times it by 100, and I can get the maximum efficiency of an item. Now, if you go buy some type of heating or coolant unit, whether it be a space heater or an air conditioning system, you'll actually see a maximum efficiency number. That's this equation. So it's the heat that it's your typical heat standards, and if it's something that's trying to make heat, it's its maximum setting, right? Based on the coldest temperatures that they feel is inventory safe within their system set. And they're setting up this number to do this basic equation. Great example of conduction and convection within itself on the window. And we're going to talk so much about windows, because windows are one of the leakiest things in a home, right? They leak so much energy right through them. So they allow a lot of that heat out. That's the importance of drapes, my friends. You don't necessarily need new windows. You just need good curtains, right? So finally, last but not least, the third law of thermodynamics, which says that if there is a state of motion within the world, there is a point with which all things that we know of will no longer have molecular motion. Everything will just be completely ultra solid. This ultra solid was something that Boseman from the Boseman-Higgs particle concept had actually idealized. And about 25 years ago, they actually came up with the actual number of absolute zero, and they found that absolute zero was 273.15 degrees Celsius. That is a state where every known thing has absolutely no molecular motion. There is no motion in any form of matter. I just thought that was funny. That brings me finally to the math and thermos. So the math questions I picked up with in math videos that are based on doing these sorts of equations, and then I'm asking you to replicate these questions again as part of your assignments for this module. And you really need to become careful. Now, some of you guys who are comfortable with this maybe have been exposed to it through chemistry classes, and I know that because as teaching this course over many, many years now, I've seen students who can fly through these equations, and then there's other students who really need to take their time and have their help. So there's videos that are set aside to do these equations and answer these questions. Take your time, work through, and if you have any questions on them at all, please post in the discussions. I'll be reading the discussions as well as other students. You're welcome to read discussions, and if you do answer anybody's questions on discussions, I do give a little extra credit on those things. So please do take a look. Please feel free to ask questions if you're getting stuck. But here are some questions that you should be able to answer on your math thermos. And then Carnot's theorem. Carnot's theorem goes back into maximum efficiency, and it basically is how do we determine the efficiency of an item. So once again, efficiency is something that you'll see on the box structure of things, and Carnot's efficiency just talks about how good is this number. Now, Carnot's efficiency is different than maximum efficiency. Carnot's efficiency tends to yield a number that is very idealized. Like this is the best of the best of the best. We're pretending this system works flawlessly with nothing that could stop it. There's no wind currents, nothing could hurt this system. It's working at its maximum. So when we see a Carnot efficiency number on anything, what you need to keep in mind is that that number is the absolute ideal. That is not the most likely reality of what you're going to be receiving in any number set. And on that note, we have worked our way through Module 4. Good luck. Once again, ask questions if you have them, and I'll see you in Module 5.